Right, welcome everyone. This is the April meeting for the East Midlands Regional Group of the Geological Society. I hope everyone has had a nice Easter. We're coming out of easing restrictions on lockdown. The sun's been out today, so things are kind of looking up. So hopefully, at some point in the future, we will be scheduling some meetings in face-to-face and maybe getting out in the field. So the picture behind me is our last field trip actually to Bradgate Park back in summer of 2019 now, so it seems a long time ago. In terms of the format follows pretty much as we've done in the past. We'll have Q&A at the end, so if everyone can remain muted for the duration of the talk. If you want to use the Q&A box really to put in your questions, do that, or we'll unmute people at the end. So tonight's presenter is Dr. Stephen Banham from Imperial College. He's a researcher there, working with Professor Sanjeev Gupta. You may have seen they've done a lot of work on the Curiosity rover on Mars. So we're tying in with the 2021 Year of Space theme, and so he's been involved with Curiosity and the geology in the Gale Crater, and although he's not involved with Perseverance, which is obviously on Mars at the moment, he is or will be, and certainly been working on ExoMars 2022, which is actually the next mission to Mars. That'll be the next rover. So just on behalf of the group and everyone present, I'd just like to thank Steve for accepting the invitation, and just delighted as well that he's been able to join us tonight to give his talk. So I'll just pass over to you, Steve, now if you want to share your screen, and we'll get underway.
I think that should be sharing, so without further ado, I'll hit F5. So these are some, this animation that's running is a series of Hazcam mosaics that were taken, sort of starting about Sol. Oh, I can't remember the Sol now off the top of my head, but this is on the run up to the outcrop at Mount Marcou. So this will be sort of Sol 3000 up to the recent up to the recent period of time. So it'll be about Sol 3027, and you can see that the arm is deploying, and we're sort of testing what the geochemistry of these rocks are as we're traversing. So I believe you should be able to see my cursor. So we can see here that there's this sort of prominent outcrop here, which is about 6 meters high, which we're getting progressively closer to. And this is where I'm hoping to finish the talk today, as this is quite an exciting location in terms of understanding the geology of Gale Crater, and also it's hopefully going to give us some great insights into sort of the formation and of the sediments within Gale Crater, and also the climate and the evolution of Mars in general. So hopefully when we get to this outcrop later in the talk, we'll have some idea about how that sort of the broad scale evolution of Mars's climate, and how Mars went from sort of a wet and humid sort of planet to the barren, desolate, dry planet that we see today. So this is just sort of a panorama showing the context. So this is Gale Crater. Start again. So this is Mount Sharp here, and then we're panning across towards the south, And this is the cliff that is known as Mount Maku. And if anybody's been on Twitter following Mars, this is the next big thing, and it's been quite popular in terms of people processing the data. And this is Mount Maku, and this is the location of the last drill site that we drilled, the Nontron drill site at Sol 3070. And this is the this is the rover parked in front of the outcrop, having drilled the Nontron drill site. Just down here, if we zoom in, we can see this is the Nontron drill hole, which is about 5 centimeters deep. And this is the last drill hole that we're going to be drilling in the phyllosilicate strata, which sort of underlies the Glen Torridon area. And the next drill site we're going to drill is hopefully on the top of this outcrop, and this will be in a completely new strata or stratigraphic unit, which is associated with a completely different phase in the infilling of Gale Crater, which hopefully will be representative of a completely different climate regime. So hopefully we'll get there during the talk. So with that, I'd like to introduce myself. I'm Dr. Stephen Banham. I'm a participant on the Mars Science Laboratory and the PanCam instrument on the ExoMars rover. I'm a little bit fried because we've just got out of a PanCam meeting, a ESA meeting to do with figuring out what the science objectives are for the ExoMars rover. So if I'm a little bit fried, that's why. And as a result, I may not talk too much about ExoMars. So we'll just focus on the geology in Gale Crater. So one of the key objectives, or sort of one of the driving ideas of exploration of Mars sort of over the last sort of 50 years is the search for extinct life and trying to determine whether Mars was habitable. We can see, looking at images of the present day surface, that Mars is a relatively inhospitable environment. There's very little water at the surface. It's dry. The atmospheric pressure is sort of about 10 millibars, and the whole planetary surface has been bombarded by cosmic rays. So it's a pretty inhospitable environment. But sort of looking back at the ancient strata, we can get an idea that this wasn't always the way. Sort of there's evidence of flowing water and a thicker atmosphere and even a magnetic field. So if we look back into the sort of the terrestrial record, back to where habitability on Earth is sort of first identified, the first signs of life, we can sort of go back to sort of about 6.5 billion years ago, where there's the first sort of undisputed examples of life on the surface, with sort of microbial mats identified in the apex chert. We can go further back into the rock record, sort of to about 4.3 billion years ago. We sort of have this zone where the blue dotted line is, where sort of there's tentative evidence of life in the stratigraphic record. There probably was life back then, but it probably wasn't established well enough to be able to change its environment or easily become preserved into the stratigraphic record. But as time went on and life became better established, it was able to better leave a signature within the stratigraphic record, and that's why we're able to find an undisputed evidence of life at 3.5 billion years ago. But there almost certainly was life before then. It just wasn't recorded in the rock record. And there's all sorts of things like possible stromatolites and carbon isotope ratios, which sort of go into this sort of hidden life era here. So if we look at this time frame here, where there was sort of putative life on Earth, and then take it up here and look at Mars's stratigraphic sort of epochs, we can see here that this time where sort of life may have been flourishing on Earth but couldn't leave a record sort of coincides with these key periods in Martian in Mars's geological record. So we have the Noachian, which is characterized by sort of persistent water on the surface, and which then sort of grades into the Hesperian, which is sort of the episode characterized by the drying of Mars. So there was evidence of surface water sort of round here, but as this period of time goes on, observations from orbit and the surface sort of identify that Mars sort of dried out in this period of time. And then from the Amazonian, which is sort of 1 billion years ago, to the present, then Mars was sort of a dry polar desert characterized by sort of very few surface processes. So the Noachian and sort of the early Hesperian are the periods of time that we want to look for extinct life, or would sort of be the best place to look for extinct life, where there was persistent surface water and potential habitable environments on the surface. So what makes a habitable environment? So you want to ideally look for the major biogenic elements. So these will be things which are the ingredients for life. So carbon, hydrogen, oxygen, nitrogen, and sulfur and phosphorus. You need energy in a habitable environment. So this can either be from the sun, if for photosynthesis, or also as well you can have chemotrophs or animals or biological activity associated with thermal vents. You also need a reaction medium, so this will be water, where all of these ingredients can sort of mix together with some sort of energy source, where all the molecules can come together and interact. And all of these things basically feed into what could be a habitable environment. And this could be sort of a lake or an ocean or sort of pore fluids underground. These could also all classify as being a habitable environment. So I'll just skip some of these slides. So one of the things that we want to be looking for are biomarkers preserved within the strata. So actually hopping back a slide, so some of the more obvious things that we could look for would be sort of microbial structures. So here's some examples of potential microbial structures from Earth from about 3.7 billion years ago. And these would be quite obvious, and it would be quite nice if we saw these on the surface of Mars. But by the time sort of microbes and life has got to a point where it can create these sorts of structures, that like life has evolved into quite a complex format as it is. So, for example, stromatolites are typically formed by sort of colonial microbes and bacteria, which are all sort of have their specific place within the environment, and bacteria will actually be stratified within the stromatolite, sort of taking light energy at different levels. So they'll actually be stratified depending on which sort of wavelengths of light that they want to take. So these are quite complex sort of microbial communities that occupy these stromatolites. So we probably actually want to look for the less obvious biomarkers. So sort of parts of phospholipid bilayers or complex organic cyclic molecules. So two good biomarkers, for example, would be these hopanoids and sterols, which are chiral molecules which you find in phospholipid bilayers. So these are examples of complex chiral molecules which typically only arise as a result of sort of biogenic processes. They typically don't form as a result of abiotic processes. So you'd want to look for these, or you'd want to look for these sort of complex cyclic aromatic compounds which will be associated with proteins, although these can, in some cases, arise abiotically. Also, as well, another good thing to look for are isotope ratios. Biological processes tend to bioconcentrate one or the other isotopes depending on the organic process. So this is another thing that you can look for. And to do this on the MSL mission, we'll use this instrument here, which is the SAMS instrument, and this is the most advanced and sophisticated mass spectrometer unit ever flown into space. So there's a gas chromatography mass spectrometry instrument, a tunable laser spectrometer as well, and then there's some other instruments that we can use for looking for these complex molecules. You can also use this as well for doing geochronology as well, if you can find igneous samples that you can drill and sample. So that's sort of an outline of what we're looking for. We're looking for sort of biomarkers in relatively old terrain. So the next question is where would you want to go on the surface of Mars? So this is a molar laser altimetry survey, which was done sort of in the late 90s, early 2000s. It's just showing the elevation of the whole surface of Mars. So there's this vast northern lowlands up here. There's the southern uplands to the south. Then this boundary, which I'm tracing out, sort of, you can see that there's sort of a dichotomy boundary between the two, and then sort of going off towards the west here, you can see that there's these volcanic features. So this is Olympus Mons, and then the Tharsis volcanic region, and then over on the east side of the map, there's also Elysium Mons as well, which is a volcanic feature. These volcanic features are relatively young; they're sort of 1 billion years old or less. There's also the Valles Marineris area here. These this sort of vast Grand Canyon of Mars, which then goes into these outwash plains in this location here. So there has been previous exploration missions which have gone. So the Viking mission landed here, sort of in Acidalia Polynesia area. There's the MER rovers, which sort of investigated the southern parts of Arabia Terra, and then Spirit over here to the far side over here. And then Mars Science Laboratory investigated Gale Crater here, which just sits on the dichotomy boundary in this white area. And this is where we'll be focusing on here. Jezero Crater is here, which is where the Perseverance rover has just landed. And then also as well, Oxyoplanum's just over here on the western edge of Arabia Terra, which is hopefully where the ExoMars mission will be landing in sort of 2022, or sorry, 2023. It should arrive there. It'll launch in 2022. And also as well, for fans of The Martian, Acidalia Polynesia is where Mark Watney was stranded. So next we'll sort of talk, I'll sort of talk about how you get to Mars and how you arrive at the surface. So it's a good opportunity to talk a little bit about the Perseverance rover as well. So Perseverance and Perseverance shares a lot of flight heritage with Curiosity. They're essentially the same chassis and quite a lot of instrument payload. It's just that they've gone and updated some of the scientific instruments and added a few extra cameras on here and there to record the descent and landing. Although one of the key differences is that Perseverance was designed as a sample cache mission, where they plan to sort of identify key samples, drill them and core them, and then put them into the belly of the rover for later retrieval during the Mars sample return phase of the mission. Whereas Curiosity's sort of does all of its analytical work on the surface of Mars. So those are the two key differences between the two missions, is that Curiosity analyzes things in situ, whereas Perseverance is designed to return the samples to Earth, or be the first part of the chain of returning the samples to Earth, where we'll use all the best analytical equipment on Earth to determine whether they're biosignatures. So here's just a quick view of both the rovers, just to show that they share quite a lot of flight heritage. They're both sort of powered by the same power unit, a multi-mission radioisotope thermoelectric generator at the back. They have similar communications array. The mast cams are mounted on this this mast here. There's also a ChemCam instrument on this one, or a advanced ChemCam SuperCam instrument on this one here. And then there's the two mast cams, and the nav cams are both located here. Both have an arm with a instrument turret on the end, which has various different instruments. The other key modification is that they made the wheels stronger for the 2020 mission, after observing all the wear and tear that happened to the wheels on MSL. So both missions arrived to Mars in broadly the same way. This is the sort of the entry phase, where we've got this ablative heat shield here. The rover would have been doing about 13,000 miles an hour when it arrived. We've got this ablative heat shield here, which slowed it down to about 1,000 miles an hour before the parachute could be deployed. The heat shield would have heated up to about 2,000 degrees Celsius on the way in. This is about 10 kilometers from the surface. The supersonic parachute was deployed. So this is the example from Curiosity. This was the first image, and then this is the second image taken by the descent imager, where the heat shield came off. Down here you can see the Banham dune field, which is in Gale Crater. This next slide is taken from Perseverance, sort of the deployment of the parachute, then the deployment of the sky crane, followed by the descent of the rover to the surface. This would have happened similarly on the Curiosity mission, where the parachute would have deployed and the rover was deployed to the surface with the same sky crane mechanism and deployment system. As Curiosity was descending to the surface, the Mars Reconnaissance Orbiter passed over the top and was able to image the rover in its descent phase with the parachute deployed as it was descending into Gale Crater. And then again, it was able to do the same with Perseverance. So this is Jezero Crater here. This is the delta, just where the cursor is here. And then as well, we can see the Perseverance descent and landing system here. We can see the parachute and the back shell here. Later, the Mars Reconnaissance Orbiter was able to pass over the top of Gale Crater, and we can see here that we've got the Curiosity rover with a lot of stirred up dust in the vicinity of where the rover was dropped off by the sky crane. And again, we can see similar sort of things with Perseverance. We can see sort of the parachute and back shell, which has been dropped off here. And then we can see the rover deployed here. These two sort of butterfly wings here are where the sky crane rocket sort of disturbed the dust and blew the dust away. This is one of the first images taken by Perseverance after landing, and we can see sort of dust disturbed by the landing and the descent system here. And this is Curiosity after it landed in Gale Crater with Mount Sharp. It's sort of off here in the distance with the Banham dune field sort of running between the landing site at Bradbury and Mount Sharp. So the next question is going back to Gale Crater. This is where Curiosity landed at Bradbury in about 2012. And then since then, the rover's sort of driven off towards the off towards the west along the Bagnall Dune field, and then it's sort of crossed here where the cursor is, and now it's driving up onto the flanks of Mount Sharp. So the next question is why do we want to go to Gale Crater? And the reason is because we believe from orbital, or believed at the time when the landing site was selected, that there was a layer cake stratigraphy here. And basically we have a layer cake stratigraphy preserved in the central peak, which is Mount Sharp, which sort of recorded how the Martian climate evolved over time. So from orbital observations using the CRISM instrument, which is a spectral, a reflected light spectrometer, we were able to determine that in the lower parts of Gale Crater there were phyllosilicate deposits, which is important because phyllosilicates typically form in association with water. So the lower parts of Gale Crater, they interpreted that there must have been some sort of aqueous environment, be that sort of an aqueous environment at the surface or diagenesis and alteration within the subsurface, which form these phyllosilicate units. And then overlying these are these sulfate-bearing strata, which are interpreted to have formed as a result of sort of more arid processes, so sort of either evaporitic processes or desiccation, not desiccation, evaporative processes where you ended up with sort of brine, salts precipitating out of a sort of a concentrated brine. So basically the lower part of the stratigraphy would have been sort of early wet Mars, and then the upper parts of the stratigraphy were interpreted to be sort of later drying out, more arid depositional conditions. So broadly, as you go younger, Mars is inferred to get drier and also as well less habitable. So basically we can look for biosignatures in the lower part, and also as well we can get a good idea of how Mars's climate changed over time as a result of the change in climate and the drying out of Mars. So and also as well, quite conveniently, Gale Crater was formed at approximately the boundary of the Noachian and the Hesperian about 3.7 billion years ago. So it sort of occupies this sort of Goldilocks zone of sort of habitability where life's going to have, hopefully would have been established for long enough to be able to sort of create a physical record within the stratigraphy. So I've noticed that I'm sort of overrunning a little bit, so I'll skip over the parts of how to drive the rover. Basically, it's a complex process where many people meet in a room, we'll select a target, we'll speak to the engineers will code the program, and then hopefully the rover will perform the operations within the code. It'll perform various tasks on the surface and then return the data. Because Mars is so far away, we can't control the rover directly, so we have to program it once a day so that the rover will perform a series of tasks. And while it's performing those tasks, we can do other things. But it's quite complicated. Yeah, so I'll skip over that and get straight to the geology. So what have we learned about Mars's ancient past, or specifically what have we learned about the environment preserved within Gale Crater? And there's quite a lot of firsts in here. There's sort of the first identified fluvial conglomerates sort of in the landing area in the Bradbury landing area. There's fluvial bar forms identified. There were first mudstones identified on the surface, There's potential for anti-dunes in the Kimberley area. Sanjeev's still working on this when he's not fully engaged with the 2020 mission. And then also as well, there's the analysis of modern dunes and modern aeolian processes associated with the Bagnall dune field. So these are just some of the highlights from the first part of the mission. But what we'll do is we'll pick up the stratigraphy here in the Pahrump Hills, and then we'll traverse along here to where the rover currently is here, sort of down by the dog leg, just adjacent to the notional route. Currently we're at this juncture between this clay unit here, which infills this this area known as the Glentorridon, known as Glentorridon, and this sulfate unit here. So we're actually at this major stratigraphic boundary here. So hopefully I'll fill you in with some of the details of the environment sort of along this traverse. And by and large, it's a tale of two formations up until this point. So there's the lacustrine Murray formation, which forms the bulk of the stratigraphy that we've traversed across, which is then unconformably overlain by the Aeolian Stimson formation, which postdates the deposition of the lacustrine Murray formation by some period of time, but we're not quite certain how long. So first we'll start with the reconstruction of the ancient lake on Mars. So this is an overview of the distribution of the Murray formation as we knew quite early on in the mission. So the Murray formation actually now goes beyond this blue line, sort of further to the south, sort of to where the cursor's waving, sort of in this area here. So all the strata within the Glentorridon area as well is associated with the Murray formation, along with this ridge, the Vera Rubin ridge here. But we'll start the story in this area called Pahrump here. So when the rover arrived at Pahrump in September 2014, around about Sol 750 of the mission, they noticed that there were quite a lot of sandy outcrops poking out from this this tan-coloured sort of low relief smooth weathering feature strata. So they decided, rather than sort of driving linearly across the outcrop, they decided to do a few circles of the outcrop to decide where to drill the samples. So this is sort of a sub area of Pahrump. What they did was they decided that they would drive along this this path here. They then decided that they would stop and do remote sensing stops here. So this was image key parts of the outcrop using the mass cam. Then after doing this drive, they then sort of drove back around and did they then drove back around and they did contact science stops at these red circles. And then on the third pass, they decided to drill at these locations based on what they saw. And this is the map of how this went down. So they sort of drove around once, collecting imaging data, and then drove around again and collected contact science data. So this is where they deployed the arm and took geochemistry using the APXS instrument, and also used the Marley camera sort of to view close-up textural details, and then they would have stopped and drilled at these various different locations here once they decided what the stratigraphy was. So kind of like what geologists do on Earth, sort of walking around looking for the best outcrops, walking back, checking again, and then going back for further samples if they need it. So one of the key things that they identified at Sol 830, so they were here for quite some period of time. So by the time these images were taken, they'd been here for about 70 or 80 sols. and they identified these beautiful sub-millimeter thick laminations here. They're quite laterally persistent, and they're well defined, and they interpreted that these were probably deposited as a result of mud or silt particles settling through a column of water out of suspension to form these lake bottom laminated mudstones. So they interpreted that these would have formed in quite a quiescent environment, such as a lake. Moving up further in the stratigraphy, they were able to identify these sandstone units as well. There were 3: Newspaper Rock, Whale Rock, and Salisbury Peak. On closer inspection of Whale Rock, they identified trough cross bedding, which indicated tractional transport of sediment along the base of a channel potentially. These cross sets were dipping to the south as well, which gave a paleo transport direction from the north to the south. And this is just an example of the dune. Sorry, I included this because the last talk was to an astronomical society, so I had to sort of give some context of why this cross-bedding was important. But in general, but from this they were able to sort of get an idea that there could have been cycles within this lake, within Gale Crater. So potentially a little bit of sequence stratigraphy. So for the lower part here, this would have been lake center deposits, but then when you have these sandy inputs here, there are 2 hypotheses. You could have either a reduction in lake water levels, so the lake contracts, and then any fluvial systems bringing sandy material in have to sort of prograde further into the lake, so you end up with accumulating fluvial deposits in this lake. You then go into a more humid period, the lake expands, you go back to depositing your distal mid-lake sediments, and then the lake level drops again, and you deposit whale rock, and then this repeats. Alternatively, rather than using this allogenic mechanism, you could also say that there's an autocyclic process which is causing this, where you have a fluvial system associated with the lake margin, and you just have the fluvial system jump in position instead of invoking lake level rises and falls. They drilled here as well. So this was the Mojave drill site on Sol 800 using the SAMS instrument, and they were able to identify these aromatic compounds, which they inferred could be sort of some precursors to sort of biological processes. So these sorts of molecules would be key components for sort of making amino acids and things like that, which could then go on to produce life. So basically from the SAM analysis, they were able to determine that there's evidence of precursors for life. So all the ingredients that you need for life are present. It just needed, but ultimately they were unable to determine whether there was actually life present. So moving on from here, we then continue along the stratigraphy. So up stratigraphy to this key unit here, the hematite ridge. So they identified this from orbit by its strong spectral signature. We've been able to map various members of the lacustrine Murray formation as we traversed up here. So there's evidence for drying out of the lake within the Blunt's Point member. Then as we go into the Pettigrove Point member and the Jura member, we see further evidence of potential drying out as well. But as we drove up, we still saw this we still saw evidence of these horizontally laminated mudstones, which are indicative of the general lacustrine environment, which we believe to have formed in Gale Crater. But what we did see was sort of a large amount of diagenetic overprinting of this strata as we were driving up onto the top of the Murray Buttes. And there was quite a strong there was quite a concentration of hematite within the ridge, which is what we think, which is what we saw from orbit. So this is just zooming in, and we still see these finely laminated bedrocks, even at this unit where we've driven up stratigraphy by several hundred meters by this point. When we get into the Jura member, we start seeing things which could be potentially crystal molds or salt pseudomorphs. So this would indicate quite strong drying out of the lake, where you have salt salt crystals precipitating within the water column and then raining down into the onto the bed of the lake, which are then buried to form these pseudomorphs. So this is sort of what we would interpret the environment to be at this point of the infilling of Gale, where we sort of have these. We've gone from a more perennial lake to more ephemeral. The strata that we saw at Pahrump Hills would be more of a perennial lake, but by the time we get up here 200 meters further up stratigraphy, we've gone into more ephemeral lakes here, where potentially with sort of salt precipitation in the margins, or salt pseudomorphs, salt crystals forming within the lake and then forming salt pseudomorphs. This is just an animation of the same sort of depositional environment, where you go from a perennial lake to more isolated ephemeral lakes. So since then, we've driven across the we drove off the back of the Vera Rubin Ridge into Glen Torridon. We explored in here. We went up onto the Stimson formation here, which I'll talk about shortly, and then we drove off to the east, past Bloodstone Hill, and eventually to this outcrop, which is Central Butte. Here we found in this layer here evidence of ripple forms, or these enigmatic dunes. Dune scale bed forms, and this is just a zoom in. They're sort of broadly symmetrical. They appear to have be formed of fine laminations, and currently our interpretation is that these may have formed sort of as a result of storms within Gale Crater. So these may represent wave deposits formed by sort of stormy activity, which is quite cool in itself, because this means that if these were wind generated waves, then the lake present in Gale Crater was not ice covered, which is what some people think is possible. So this brings us to where we are roughly now, which is Mount Marcoux. So the Nontron drill site is at the base of the cliff, and since then the rover's driven onto the top of Mount Marcoux, and it's somewhere on the top here. And this is where we're planning to drill the next where we're planning to take the next drill site within the next few sols. So this is actually quite striking, because in this image here we have quite plainly, or if we zoom in here, we can see that we've got well laminated strata at the bottom with few fractures, or relatively few fractures. You can trace these laminations across the outcrop. There are variations in the lamination thickness, which may be related to variations in amount of sediment brought into the lake at various times. People are actually working on the variations in thickness to see if there's any cyclicity. But as soon as you go above this yellow boundary here, you can't see any of these laminations, and you go into this sort of massively overprinted and fractured unit here, which we're about to sample. So we're actually thinking that this could be the bound, or at present we think this could be the boundary between sort of the phyllosilicate units that we see in the lower part of the stratigraphy, and the sulfate-bearing strata that we see in the upper parts of Mount Sharp. So this could be sort of notionally the boundary between sort of early wet Gale Crater and later more dry and arid Gale Crater. But we'll have to wait and see what the results are before I can say that with any or give a definitive answer. So these are some images just taken in the last few sols. So this is driving round the corner, and this was actually taken yesterday, about 12 hours ago. Sorry, maybe 48 hours ago. And this is the top of Mount Mercou. I tried to process an image of this, but unfortunately I ran out of time. But this is the view of Gale from the top of Mount Mercou. So this is sort of the cliff edge that you could see from the previous image. So there's about a 6 meter drop off the edge here. This over here is the crater rim over here, which is about 40 kilometers away, and then this is Mount Sharp over here in the distance, several kilometers away. And then hopefully the rover in the course of the next few months and years is going to drive sort of off in this direction up into the Geddes Vallis area to investigate the sulfate bearing strata in more detail. So this now, so also as well, off in this direction here is a capping unit which overlies all of these Murray Formation deposits. So I've just looked at my watch, we've got 10 minutes left. So I can either stop and take questions, or if you want, I can talk about the Stimson dune field which overlies these deposits. So I'll take a break here and ask for your advice.
Hi, Steve. I'm fine with you carrying on. You know, that's fine. You know, if you want to, that's perfectly fine. Unless you feel that you've had enough, of course.
No, I can carry on. So this is getting to the exciting stuff, which I've actually been working on.
Okay. Yep.
So overlying the lacustrine Murray Formation is the Stimson Formation. So we're now on to the second part of the story. So on Sol 978, which is approximately when I joined the mission, so I wasn't involved with the mission right from the start. So a lot of the stuff at the Pahrump Hills happened before I arrived on the mission. But I arrived from my job at the British Geological Survey round about this time, and was put to work on sort of looking at what was in sort of the rover's area. And round about this time, we came across this this stratigraphic unit here, which is known as the Stimson Formation. When we first saw it, we weren't quite sure whether it was conformable to the Murray Formation or whether it was unconformable, or what was going on. But we could see that there was this major change in lithology here. We've got the Murray Formation down at the bottom here, where it's sort of this tan-coloured, smooth weathering, sort of not particularly weathering resistant unit, and then overlying it with this sort of strong boundary here, which we later determined was an unconformable boundary. We've got this well-bedded, dark-coloured sandstone which is cliff forming overlying it. For the astronomers, I had to put this diagram in, but we have an unconformable surface. So this just shows the different outcrops of the Murray Formation, sorry, the Stimson Formation that we've been looking at. So the Stimson Formation was first identified over here at Marius Pass, just sort of in this area. The previous image was taken just by the Emerson Plateau. And then as the rover's driven south towards the foothills of Mount Sharp, it sort of drifted in and out of the Stimson stratigraphy. So it sort of drove up into the Stimson Formation here, and then dropped back down onto the Murray Formation here, and then drove up onto the Stimson here, then past the Stimson here, and eventually it got to the Green Cube Pediment, which we weren't sure what it was until we got there, and then it turned out to be Stimson Formation as well. Now the really cool thing is that the Stimson Formation sits on an unconformity, and this unconformity sort of mantles about 150, no wait, sorry, about 300 meters of the Murray Formation. So as we go to the south here, we can see that the unconformity sort of mirrors the, or vaguely mirrors the profile of the traverse, and we've got Stimson Formation unconformably up here and down here as well. So this strata sort of sits on this paleo surface with about 300 meters of relief over about 2 kilometers of traverse from the north to the south. So what is the Stimson Formation? So at Williams Outcrop, we were able to do one of the most detailed investigations of the Stimson Formation at the time. So we drove up to this outcrop, and we were able to identify that there were that the Stimson's composed of cross-bedded sandstones, and on closer investigation, we can see here that we've got thin, laterally persistent laminations, and we interpreted that these were potentially wind ripple laminations, just because of their uniform thickness, which you could sort of trace out for several meters from the basal bounding surface to the upper base, or sorry, the upper bounding surface. We were able to deploy the hand lens imager to look at the sedimentary texture of these sandstones, and we could see here that we've got these this bimodal sorted sandstone, where the sand grains were much more well-rounded than anything else that we saw up until this point, and we had a mean grain sizes of about 400 microns for these samples. This is just an example showing here that we've got these really well-rounded the sand grains in here. We then sort of interpreted the outcrop. We're able to see that we've got these simple cross sets with a where the cross sets have a dip azimuth towards the northwest, sorry, the northeast, and we were able to reconstruct, and also as well, these cross sets were about sort of on the order of about 0.5 meter to 1 meter thick. The cross sets that we saw at Pahrump were sort of on the order of about 5 or 10 or 15 centimeters thick. So these are sort of much thicker than the fluvial cross sets that we've seen. From this, we were able to infer that we had aeolian dunes, which were about 10 meters high with wavelengths of about 0.5 kilometer. They were probably sinuous crested dunes, and then they may have had and then on these you had wind ripple strata sort of accumulating, or sorry, wind ripples migrating across the lee slope, which generated the wind ripple strata, which is characteristic of much of the Stimson Formation in here. We then carried on south to the Murray Buttes. So I'll show a few examples of the cross strata that we saw at the Murray Buttes here at Butte M4. And And if we look at the west side of Butte M4 and zoom in, things look a lot more complicated than what they were at the Emerson Plateau. So we started by interpreting the cross laminations. We looked for truncations and different bounding surfaces. We were able to identify 2 orders of bounding surface in here. We were able to identify these subset bounding surfaces here in yellow, which are inclined, and then we were able to identify these compound set bounding surfaces, which are sort of sub-horizontal and more laterally extensive. So these broadly coincide with interdune surfaces, so the migration of a dune, and then these subset bounding surfaces we interpreted to be superposition surfaces, which were formed by superimposed dunes migrating across the lee slope of larger primary dunes or draws. And again, from the north side, we were able to sort of trace these different surfaces around the corner, and we were able to confirm that these were bounding surfaces scoured by superimposed bed forms, just because of the geometric relationship of the bounding surfaces and the cross laminations. Just skipping down to Butte M12, which is at the southern part of the traverse. And again, we were able to identify these sort of bounding surfaces in here, although the stratigraphy here is much more complicated. And from these, we were able to reconstruct the dune forms. So from this, we were able to identify that we had large primary dunes or draws, which had smaller superimposed bed forms migrating across them. The large draw scale bed forms were migrating towards the north or the north-northwest, and then the superimposed bed forms were migrating across the lee slope towards the northeast. We've actually got a paper coming out on this in the next few days, sort of detailing the reconstruction of the dunes in the Murray Buttes and how we came to these conclusions. But broadly, this is what we think the Stimson dune field may have looked like at the Murray Buttes area. We've got these large draw scale bed forms with superimposed bed forms migrating across the lee slope, and then we've got these other superimposed bed forms migrating perpendicular to the draw crest line, sort of in here. And this is as a result of either a bimodal wind regime, or as a result of a sort of a boundary layer effect, where you end up with like a smaller wind regime, a localized wind regime in the lee of the dune, which drove these superimposed dunes along the lee slope. Eventually, we've got up to the green hue pediment, which is what I'm currently working on now. Without going into too much detail, this is sort of a panorama of the pediment area. We've got Tower Butte here, which is composed of compound cross sets. We've got the Murray Firth outcrop here, which is also composed in the lower part by compound cross sets. But on the top of it, we've got planar simple cross sets. If we jump up onto the top of the pediment, we can see this image here. So the Murray Firth outcrop, which is composed of compound cross sets, is just underneath here. And then we've got these planar cross sets just in here. And the planar cross sets, we've been able to reconstruct that we have simple dunes at this location where we have seasonal variations in wind. So if I just go back to this slide here, unfortunately I don't have the zoom in of this area here, which is called the Edinburgh section, but you can see sort of intercalated avalanche strata and wind ripple strata. So the wind ripple strata are sort of these weather in structures, whereas the wind ripple strata are these weather in proud layers. And what we're able to infer is that we have seasonal wind variations where you have wind transporting sediment normal to the dune crest line at some periods or during some parts of the season, where you have avalanche strata accumulate, but then the wind regime sort of shifts at some part of the season, so that the wind is oblique to the dune crest, which is then the period of time where you have wind ripples driven sort of obliquely across the lee slope of the dune, obliquely to the crest, which is where you then get the wind ripple strata forming. And we're able to see sort of about maybe 10 cycles where the wind has shifted and resulted in this this switch from accumulating avalanche strata on the lee slope to accumulating wind ripple strata on the lee slope. Hopefully the paper on this will come out sometime in the summer, but this is the paper that I'm working on now. So that brings us to the end of the talk, and sorry it was a little bit incoherent, but yeah, I'm a little bit fried. So with that, I'll take any questions about the presentation.
Thanks, Steve, for that. That's just it's just amazing, really, when you think about the images and the information and the quality of that we get back. You know, given that Mars is sort of 220 million kilometers away from us, and I mean it's mind blowing, really. So yeah, I don't know if we've got any questions. I was just looking. There's nothing in the chat box there. I sort of asked people if they wanted to put, but yeah, if people want to put their video on and unmute themselves, that's maybe how it. Tim, have you got a question? Yeah, I can see you waving.
Yes, can I ask? A brilliant talk, Steve. Absolutely fantastic. Really, really exciting. Can I ask if any dating work's been done on the phyllosilicate rocks? Like you could use argon-argon or potassium-argon dating. Have you got any results from those rocks yet?
I don't think anybody's been able to do any argon-argon dating on the phyllosilicates, but they did find a igneous class somewhere near the start of the traverse, which they think was derived from the basement somewhere near the crater rim, and I can't off by heart remember what the date was that they found when they were able to do it. But yes, they have.
It all depends on the spectrometer that's been instrument that's on the lander, so I'm not sure what the capabilities would be.
Yeah, but the short answer is they've not been able to do any geochronology on the mudstones, but they have been able to do geochronology on one thing in the crater. So it is possible.
Great.
Steve, I've got a question here from Tommy on the chat. He's asking about, you mentioned stable isotope data, and the question is, has there been any isotope data from Mars to indicate the signature of life?
I don't think there has been yet, and also as well, that's the domain of the geochemists as well, and I'm much more of a sedimentologist, so I don't think they have found any isotope data indicating life.
Right, yeah, fair enough. Mike, have you got any questions?
No, it was a brilliant talk. I'm kind of blown away. It's just amazing some of the things that have been done at such a remote distance. Brilliant.
I've got a question, Steve, actually.
Yeah.
While we're waiting for anyone else. Just wondering about how the sediments sort of actually accumulate, because I'm just sort of thinking, Mars, I'm pretty sure that we think there's never been sort of plate tectonics and that kind of sort of activity happening there. And I just wondered how lake deposits and things have been preserved and been able to go through sort of diagenesis and sort of remain in place.
Yeah, so the major basin forming process is actually by cratering. So most of the sedimentary basins on the surface are, or particularly, or in the case of Gale Crater or Jezero, is that you have a meteorite impact generates a hole, and then surface processes sort of transport sediment into those, be that sort of fluvial processes or aeolian processes. So you're right in saying that there's been either little or no tectonics on the surface of Mars, which would sort of generate your grabens that you would typically think as like a sediment source. However, I've just been involved in a paper on Valles Marineras, which looks at fault systems bounding the Valles Marineras, and we've actually seen that there were faults that moved, and that there was syntectonic sedimentation associated with those faults as well. So, like in general, there was no sort of plate tectonics on the surface of Mars, or that there's no evidence for it. But then at the same time, there is evidence of sort of small scale fault processes on the surface.
Great, yeah, and I think like some of the images that you see from the, because there's obviously satellites moving around, isn't there? Obviously, over Mars, and you see long lineaments and things at the surface, sort of, yeah, long sort of, I don't know what are they, like transform faults or. I've got a question from Anthea. She's asking how big. This is about the rovers. How big are they, and do they remain operational indefinitely?
So Curiosity and Perseverance are about the size of a Mini Cooper. One of the new Mini Coopers, the BMW Mini Coopers, they're about 2 meters wide, and the mast's about 2.2 meters off the surface, and they weigh about a ton, so 900 kilograms. The Curiosity, sorry, the Perseverance rover is a little bit heavier than Curiosity. Earlier rovers were a little bit smaller, and the ExoMars rover is going to be about 350 kilograms, I think. So it's a relatively small rover compared to Curiosity and Perseverance. Can they operate indefinitely? Unfortunately, no, because they'll eventually wear out. So one of the earlier MER rovers was able to run for 15 years because it was solar powered. So basically it was able to recharge its batteries using an external power source, basically. And that's why it was able to sort of carry on for 15 years, which is like 14 and a half years longer than its planned shelf life. And the reason why it was able to carry on as well is because the area where it landed was quite windy. So every time the solar panels accumulated too much dust, fortunately there would be a big sort of windstorm, or there'd be more wind in the region, or it would get hit by a dust devil, and that would sort of suck or blow the dust off the solar panels, allowing it to sort of carry on its mission. For Curiosity and Perseverance, the rover's lifetime is ultimately limited by the half-life of the 4 kilogram chunk of plutonium that's sat in the MMRTG in the back. So I think the lifetime of the plutonium, I think, is about 12 years, and as that plutonium sort of degrades through radioactive decay. So the radioactive decay gives off heat, which powers a thermocouple, which is what the rover uses to charge its batteries. But as the plutonium decays, then there's less and less heat energy made, which will ultimately mean that at some point in the near future, there'll not be enough heat energy to power the thermocouples, which power the Curiosity rover. And I think there's probably about another 3 or 4 years left in Curiosity before there's not enough not enough heat to power the rover.
Right. I can see Mike's got his hand raised. Mike.
Yes. One quick question that occurred to me. You quite often hear stories about people picking up meteorites, having meteorite expeditions to deserts. I just wondered whether you had spotted, or anyone had spotted any meteorites on the surface, or whether the wind is such that they would have drawn up sand that would have covered them very quickly.
Yes, they have. So I think they've identified at least 40 meteorites on the surface. So John Bridges at Leicester University is the keeper of the meteorites database, and they've identified quite a few on the surface. They use the multispectral filters on the mass cam to identify them, and I think the spectral signature. I can't speak much to the spectral signature, but basically they can look at it and tell that it's like an iron meteorite from its reflected spectra. But yes, we have found meteorites on the surface.
Thanks. Thank you.
Unfortunately, because the meteorites are sort of really unstable, we haven't been able to drill into them and take a sample. Also, as well, they'll probably be too hard for drilling as well. They'd probably damage the drill bit.
Right.
Mike, I don't know. Can you see the Q&A? We usually have a Q&A. I don't know. I don't seem to be able to see it.
No, all I could see is the chat.
Yeah.
We're caught up on the chat, I think.
Yeah. Okay. Just you just mentioning, Steve, about the drilling, and I don't understand that Perseverance can drill deeper than Curiosity, and I just wondered whether, obviously with Curiosity, it's travelled over the surface, and obviously if you've got dipping strata, then you don't really need to drill particularly deep. You know, you just move around, and as long as you can drill frequently enough, you know, obviously you can sample everything. But I think obviously Perseverance is, you know, one of the key things there is looking for life, and is that the reason why it drills deeper, or is it just because it's improved?
So the Perseverance rover can drill, I think it's about 10 or 15 centimeters, but so one of the differences between the Curiosity and Perseverance rover is that Curiosity uses like a masonry drill bit to drill about 5 centimeters down into the subsurface, and as it's drilling, it powders the rock, which can then be ingested into the SAM and Kim instrument. So it basically creates a rock powder, which it can then put into XRD and the other spectrometers. Perseverance is designed to take a core sample, which is then going to be put in a hermetically sealed tube, which can then be collected by a fetch rover and returned to Earth eventually. So those are the two differences in the missions, is that Curiosity does its analysis in situ, whereas Perseverance is a sample caching mission, and hopefully in 2025 or 2026, 2026, there'll be a fetch rover sent, which will go around and collect these hermetically sealed tubes, which will then be launched into orbit, and then around about 2030, the capsule with these tubes in will be collected by a return orbiter and then returned to Earth, and hopefully these samples will be delivered to somewhere in Utah, and then to a geochemistry lab near you. The ExoMars rover, on the other hand, it's got a really big drill bit on it. So the ExoMars rover is designed to drill to a depth of about 2.5 meters to collect samples. And the reason for that is because Mars has such a thin atmosphere. There's a lot of cosmic bombardment from solar radiation and cosmic rays. These are able to penetrate to about 2 meters into the subsurface before the radiation stopped by the shielding effect of the overburden. So the idea is that the ExoMars rover is going to drill down to about 2.5 meters depth and sample material from beneath this interval of cosmic radiation damage, and hopefully get some fresh samples where if there are any organic molecules, they're not going to have been sort of disassociated and destroyed and damaged. And then it's going to use a few instruments that it's got in its ultra clean zone. There's a couple of spectrometers and a Raman spectrometer in there that it's going to be able to use to look for organic molecules.
Great. I've just got just a quick one from Tommy again. He's asking whether there's been any missions to the Hellas area.
I'm just going to double check, but I don't think so. There might have been missions to near Hellas, but not actually into the Hellas basin. So this is another problem which I didn't touch on for the exploration of Mars, is that the places that we can actually go to are severely limited by engineering constraints. So we can only easily land a rover in the equatorial region, so sort of plus and minus 10 degrees from the equator. If you want to go further north or further south, it can be done, but you have to go into orbit around the planet and then change your orbit over a period of time. So when any orbiter arrives at Mars, it goes into an equatorial orbit, and then you have to change its trajectory over the course of several months until it's in a polar orbit. So if you want to get to sort of the poles or further north, sort of where Viking 2 is in the Utopia basin, you have to go into orbit and then change your orbit before you land. This adds complexity to the mission, so they don't like doing it because it's more chance of a failure. So typically for the sort of Pathfinder MER rovers, MSL and Perseverance, they basically just come straight in at the planet and don't even go into orbit. They just go straight down to the surface. And that's one of the reasons why sort of most of the missions are sort of focused in this equatorial region. The other problem is altitude as well, and you can't land in any of these high regions because there's not enough atmosphere to slow the rover down. You sort of have to aim for these lower locations where you've got much greater thickness of atmosphere to fall through, and then you can use that atmosphere to slow you down from 17,000 miles an hour to about 1,000 miles an hour before you can throw the parachute out without shredding it. And then you've still got to slow down from 1,000 miles an hour to about 200 miles an hour before you deploy the sky crane. And then you've got to slow down from sort of 200 miles an hour with the sky crane to like less than a walking pace before you can drop the rover off. An interesting fact is that with MSL, when they deployed the parachute at about 5 kilometers, they deployed the parachute at less than 5 kilometers above the surface. At that point, the thing had fallen into the crater. So when they activated the sky crane, they were below the level of the crater. In fact, the parachute could have even not deployed until they'd fallen into the crater. But that gives you an idea of sort of the margins that you have to deal with in terms of getting to the surface.
Great. Okay. I don't see any more questions in the chat. If there's anyone wants to ask anything, if you want to unmute yourself now and or just take last question maybe. Is anyone there? No. Doesn't look like anyone's coming forward with anything. Okay. Well, one quick question for me, because I did pick this up. You've got a slide showing some cake on it, and I just wondered how many publications you got in the Journal of Planetary Baking.
That's the joke slide that we keep on adding in.
Oh dear. So you're a competent baker then? You must be.
No, I'm not. It was actually a joke slide that Sanjeev made. So Sanjeev, who sat in the background here, sent me a picture of a cake while he was at one of his one of the team meetings. So I annotated it and sent it back to him.
Yeah,
But
well,
it's a good
it's always a good excuse, isn't it, for a cake at a meeting? That's, you know, that's
yeah. For anybody who's interested, the results from the Murray Buttes, where we reconstructed the dune field or part of the dune field, that should be published open access in JGR in the next week or so. So I can send you a link and a DOI to that if anybody's interested. If nothing else, the pictures are spectacular.
yeah.
But it also demonstrates as well that we're able to do sort of terrestrial level detail analysis of the strata on Mars. We've sort of shifted from sort of, oh, look, that feature could be this, to being able to do detailed studies which would stand against a study that you would do on Earth.
Great. Yeah, I mean, yeah, if anyone's struggling to get in touch with Steve, you know, just contact us and we'll pass on any questions or any requests. So yeah, I think we'll sort of draw things to a close there. So thanks, Steve, for that. That's just amazing science, and you know, really pleased that you've been able to sort of take the time out to join us. You know, it's really busy. I know when I contacted Sanjeev to start off with, I know he was really busy. So really thank you for coming and sharing that with us. So thanks very much.
I'd just like to apologise that everything was a little bit incoherent, but I came out of a meeting about an hour before I presented this, so I was sort of throwing slides together as I checked the email to see that I was supposed to be starting at 5, not 6.
Yeah, no, that's fine. Okay, okay. So just so thanks, Steve, for that. We'll close the meeting then. Just to say that the next meeting is on the 11th of May. That's right, isn't it, Mike? We've got Mark Hudson coming. It was the first talk that was cancelled actually because of COVID. So he's going to be looking at. He does lots of void scanning, and so it's going to be all of that nature. That's right. Yeah. Okay.
No, it was a talk strongly recommended by one of our members. So many thanks to Jeff, actually.
Great. Okay.
Okay.
Just
go
on, Mike. Yeah.
I was just going to say, we want to have a very brief and really only probably 5-minute committee meeting afterwards. So when people leave, could any committee who are available, and I'm sorry it's short notice, just stay on the Zoom call. Thanks.
Yeah, lovely. Thanks, Steve. Sorry we couldn't be in person, but hopefully that's going to change.
Next time, hopefully for when ExoMars arrives at Mars.
That's right. You can come back and tell us all about it. Lovely. Thanks very much.
Thanks very much indeed.